Welcome to the Whispering Universes. Before we begin tonight, I'm curious, where are you watching from right now, and what time is it there? Are you winding down after a long day, tucked into bed with the lights low, or perhaps you're on the other side of the world, where dawn is just beginning to break? Wherever you are, whatever hour has brought you here, I'm genuinely glad you're with us tonight. If this is your first time here, welcome. If you've been with us before, thank you for coming back. It's become a bit of a tradition to humbly ask, if you enjoy what you find here, would you consider liking this video or subscribing to the channel? I know the algorithm is this mysterious force that governs what gets seen and what doesn't, and honestly, I understand it about as well as I understand the finer points of tensor calculus after a long day. But your support, your likes and subscriptions, they genuinely help keep this little corner of the internet alive. To those of you already subscribed, truly, from the bottom of my heart, thank you. You make this possible. Now, I should probably offer my usual disclaimer. Despite my very best efforts to make these videos soothing enough to help you drift off into peaceful sleep, I have this terrible track record of accidentally keeping people awake instead. There's something about cosmic mysteries and existential questions that doesn't always play well with the whole falling asleep thing, but we try. And if I do keep you awake tonight, at least you'll have learned something fascinating about one of the most intriguing places in our solar system. That's a fair trade, isn't it? Tonight, I want to start with a question that might seem simple at first, almost childishly simple. What is life? Not in the philosophical sense, not about meaning or purpose or why we're here, but in the most fundamental, biological, chemical sense. What makes something alive rather than not alive? You might think the answer is obvious. Living things grow, they reproduce, they respond to their environment, they take in energy and use it to maintain themselves. These are the characteristics we learned in school, the checklist that supposedly defines life. But here's where it gets strange, where the familiar becomes unsettling if you think about it long enough. If you define life by those characteristics, then consider this peculiar fact. Right now, roughly 390 million miles from Earth, give or take depending on where our planets happen to be in their orbits around the Sun, there's a moon. Not our moon, but one of Jupiter's many moons, one of dozens that orbit that massive gas giant. This particular moon is called Europa. Europa is frozen. Its surface temperature hovers around -260 degrees Fahrenheit, cold enough that carbon dioxide would be solid, cold enough that any exposed liquid water would freeze almost instantly. The Sun, from Europa's perspective, is just a very bright star in the sky, offering virtually no warmth at all. Jupiter's immensely powerful magnetic field bathes Europa in intense, deadly radiation, charged particles that slam into the surface at tremendous speeds, radiation that would kill any surface life we can imagine within moments, perhaps within seconds. The entire moon is wrapped in a thick shell of ice, kilometers upon kilometers of ice, crisscrossed with long cracks and strange ridges, looking more like a shattered marble, like damaged porcelain, than anything that could possibly harbor life. And yet, and this is the remarkable thing, scientists are more excited about the possibility of life on Europa than almost anywhere else we've looked beyond Earth. More excited than Mars, despite its ancient riverbeds. More excited than Titan, despite its lakes and thick atmosphere. Europa, this frozen, radiation-soaked, seemingly inhospitable world, might be one of the very best places in our entire solar system to search for life. How can that possibly be? How can a frozen moon orbiting a gas giant in the cold outer reaches of our solar system, so far from the sun's warmth, be considered a potential oasis for life? That contradiction, that beautiful, profound contradiction, is what we're going to explore tonight. The question driving us is this: is there life on Jupiter's icy moon Europa? And perhaps more importantly, what does our search for life there tell us about life itself, about what it means to be alive, about where life can exist, and how it might emerge in the most unlikely corners of the cosmos? Because here's the thing that makes Europa so special, so tantalizing to astrobiologists and planetary scientists. Beneath that thick shell of ice, beneath the frozen, radiation-blasted surface, Europa almost certainly has something extraordinary. It has an ocean. Not a small lake, not pockets of liquid water, but a global ocean of liquid water, an ocean that might be deeper than all of Earth's oceans, an ocean that has probably existed for billions of years. stable and persistent, hidden away beneath the ice, like a secret the moon has been keeping since the dawn of the solar system. And where there's liquid water, where there's energy, where there are the right chemical ingredients, there might be life. Not intelligent life, probably not anything complex or multicellular, but life nonetheless. Microbial life, single-celled organisms, perhaps similar to the bacteria and archaea that thrive in Earth's deep oceans, in places where sunlight never reaches, in environments we once thought were completely sterile and lifeless. The possibility that we might find life on Europa, that we might discover a second origin of life in our own solar system, independent from Earth, would be one of the most profound discoveries in human history. It would fundamentally change how we see ourselves and our place in the universe. It would tell us that life is not a cosmic accident, not a one-time miracle that happened only on Earth, but rather a natural consequence of chemistry and physics under the right conditions. It would suggest that the universe might be absolutely teeming with life, that among the trillions of planets and moons scattered across billions of galaxies, life might be common, even abundant. But we're getting ahead of ourselves. Before we can talk about whether life exists on Europa, we need to understand Europa itself. We need to understand where it came from, what it's made of, why it has an ocean, where that ocean gets its energy, and what conditions might exist in those dark, cold waters beneath the ice. We need to think carefully about what life requires, about the chemistry and physics that make biology possible. And we need to talk about how we're actually going to search for life there, about the missions we're sending, the instruments we're using, the questions we're trying to answer. Tonight's journey is going to take us from the birth of our solar system, billions of years ago, through the discovery of Europa and the gradual realization that it might harbor an ocean, to the cutting-edge science happening right now as we prepare spacecraft to explore this mysterious moon in unprecedented detail. We'll think about life in Earth's deepest oceans, about how organisms survive in darkness without sunlight, and what that tells us about the possibilities on Europa. We'll explore the evidence for Europa's ocean, the sources of energy that might sustain life there, and the incredible engineering challenges of searching for biosignatures on a world wrapped in ice and bathed in radiation. So settle in, get comfortable. Let your mind drift with me across the vast distance between Earth and Jupiter, out to this strange, beautiful, frozen moon that might just harbor one of the most important discoveries humanity will ever make. And let's see if we can't make the familiar strange tonight. If we can't look at life itself with fresh eyes and ask ourselves what it truly means to be alive, and whether we're alone in experiencing it. Let's begin at the very beginning, because Europa's story is intimately woven into the larger story of Jupiter, and Jupiter's story reaches back to the very birth of our solar system itself. About 4.5 billion years ago, there was nothing here where we are now. No sun, no Earth, no Jupiter, no Europa. There was just a vast, diffuse cloud of gas and dust drifting through space, cold and dark, the remnant of previous generations of stars that had lived their lives, died in spectacular explosions, and scattered their elements across the cosmos. This cloud, what astronomers call a molecular cloud, or solar nebula, was composed primarily of hydrogen and helium, the most abundant elements in the universe, forged in the Big Bang itself. But mixed in with that hydrogen and helium were heavier elements: carbon, nitrogen, oxygen, iron, silicon, all the elements that make up planets and life. Elements that had been created in the nuclear furnaces of earlier stars and then expelled into space when those stars died. We are, quite literally, made of star stuff, as Carl Sagan so eloquently reminded us. Every atom in your body, except for hydrogen, was forged inside a star that exploded long before our sun was born. This cloud began to collapse. Perhaps it was triggered by the shockwave from a nearby supernova, a dying star's last violent gasp that compressed the cloud enough to overcome its internal pressure and start the gravitational collapse. Or perhaps the cloud simply reached a critical density where it became gravitationally unstable and began to fall in on itself. Either way, once the collapse started, it accelerated. The center of the cloud grew denser and denser, and as it compressed, it grew hotter and hotter, converting gravitational potential energy into thermal energy. Eventually, after perhaps 100,000 years of collapse, the center of the cloud reached a temperature and density so extreme that nuclear fusion ignited. Hydrogen atoms were crushed together with such force that they fused into helium, releasing tremendous amounts of energy in the process. A star was born. Our sun flickered to life, and suddenly there was light and heat where before there had been only cold darkness. But not all of the material in the original cloud fell into the newly formed Sunday. Conservation of angular momentum meant that the rotating cloud flattened into a disk as it collapsed, a spinning disk of gas and dust orbiting the young star. This protoplanetary disk, as we call it, contained only about 1 or 2% of the total mass of the original cloud. The sun claimed the rest. But that small fraction that remained in the disk, that was where the planets would form. And this is where the story gets interesting for us, because the conditions in different parts of this disk were dramatically different. Close to the sun, temperatures were scorching, hot enough to vaporize rock. Only the most refractory materials, metals and silicates with very high melting points, could condense into solid grains this close to the star. This is why the inner planets, Mercury, Venus, Earth, and Mars, are rocky worlds, composed primarily of iron, magnesium, silicon, and oxygen. But farther out from the sun, beyond a certain distance that astronomers call the frost line or snow line, temperatures dropped below the freezing point of water, and suddenly, a whole new world of possibilities opened up. Out here, beyond about 3 to 5 times Earth's distance from the sun, water could freeze into solid ice. So could methane, ammonia, and other volatile compounds. These icy materials were far more abundant in the original cloud than rocky materials, so there was simply much more solid material available to build planets in the outer solar system than in the inner solar system. This is why Jupiter is so enormous. Jupiter formed just beyond the frost line, in a region where there was an abundance of solid material, both rock and ice, to build a planetary core. That core, probably about 10 to 15 times the mass of Earth, formed relatively quickly, within a few million years. And once it reached a critical mass, its gravity became strong enough to capture and hold onto the surrounding hydrogen and helium gas that still filled the protoplanetary disk. The gas fell onto the growing proto-Jupiter in a runaway process, and Jupiter ballooned to immense size, eventually accumulating more than 300 times the mass of Earth, more mass than all the other planets in our solar system combined. Jupiter became so massive that it almost became a star itself. If it had been about 80 times more massive, its core would have reached the temperature and pressure needed to ignite hydrogen fusion, and we would live in a binary star system. But Jupiter fell just short, and so it remains a planet, albeit an extraordinarily large and influential one. Jupiter's formation had profound effects on the rest of the solar system. Its immense gravity stirred up the orbits of nearby objects, flinging some into the inner solar system, ejecting others out of the solar system entirely. It probably prevented a planet from forming in what is now the asteroid belt, its gravitational influence constantly disrupting the accretion of planetesimals there. Jupiter's gravity even influenced Earth's orbit, and some scientists think that Jupiter's presence was crucial for making Earth habitable, perhaps by deflecting comets and asteroids that might otherwise have bombarded the inner solar system more frequently. But Jupiter didn't form alone. As Jupiter grew, it was surrounded by its own smaller disk of gas and dust, a circumplanetary disk, similar to the Sun's protoplanetary disk but much smaller. And within this disk, moons began to form through the same process that planets formed around the Sunday. Solid particles collided and stuck together, gradually growing into larger and larger bodies. The 4 largest of these moons, the ones that formed earliest and closest to Jupiter from the circumplanetary disk, are Io, Europa, Ganymede, and Callisto, collectively known as the Galilean moons, after their discoverer. Galileo Galilei observed these 4 moons in January 1610, just a few months after he had first turned his improved telescope toward the heavens. On the night of January 7th, he noticed 3 small stars near Jupiter, aligned in a row. The next night, they had moved. Over subsequent nights, he observed 4 such objects moving back and forth around Jupiter, sometimes disappearing behind the planet, sometimes passing in front of it. Galileo quickly realized what he was seeing. These were not stars at all, but moons, worlds orbiting Jupiter, just as, he believed, the planets orbit the Sunday. This observation was revolutionary, and I mean that in both senses of the word. It was revolutionary scientifically because it proved that not everything in the cosmos orbited Earth. Here was direct, observational evidence that other centers of motion existed in the universe. It dealt a serious blow to the geocentric model of the solar system, the ancient idea that Earth was the center of all creation, and it was revolutionary in a more literal sense too. The observation that Jupiter had moons that revolved around it supported the Copernican heliocentric model, the idea that Earth and the other planets revolve around the Sunday. This was dangerous knowledge in 1610. The Catholic Church officially held to the geocentric model, and Galileo would eventually face trial for his support of heliocentrism. But the evidence was there in the sky for anyone with a telescope to see. Jupiter had moons. Things orbited things. Earth was not the center. Europa, one of those 4 moons Galileo saw, is the smallest of the Galilean moons, though still a substantial world by any measure. It's about 90% the diameter of our own moon, roughly 1,900 miles across, making it the 6th largest moon in the entire solar system. Its mass is about 65% that of our moon. If Europa orbited the Sun instead of Jupiter, we would probably call it a planet, albeit a small one. But Europa's size is not what makes it special. What makes Europa extraordinary, what elevates it to one of the most important objects in our solar system for astrobiology, is its composition and what lies beneath its surface. And to understand that, we need to talk about water, about what it is, why it matters, and why finding it elsewhere in the solar system is such a big deal. Water is a molecule, a compound made of 2 hydrogen atoms bonded to 1 oxygen atom, H2O. The atoms are arranged in a bent shape, with the 2 hydrogen atoms on one side and a lone pair of electrons on the other side of the oxygen. This asymmetry, combined with oxygen's tendency to hog electrons more than hydrogen does, gives water a slight electrical polarity. The oxygen end of the molecule has a partial negative charge, and the hydrogen end has a partial positive charge. This polarity is what gives water its remarkable properties, properties that make it uniquely suited for life. Water is an excellent solvent. Its polar nature allows it to dissolve a vast array of substances, from salts to sugars to amino acids. Inside your cells right now, thousands of different molecules are dissolved in water, floating around, colliding, reacting. Water provides the medium in which the chemistry of life occurs. Water also has a high heat capacity, meaning it takes a lot of energy to change its temperature. This makes water an excellent thermal buffer. Organisms made mostly of water don't experience wild temperature swings. Oceans store enormous amounts of heat and help regulate Earth's climate, and water has unusual density behavior. Most substances are densest in their solid form, but ice is less dense than liquid water, which is why ice floats. This seemingly trivial fact has profound consequences. When lakes freeze in winter, they freeze from the top down, and the ice layer insulates the liquid water below, allowing aquatic life to survive the winter. If ice sank, lakes would freeze solid from the bottom up, killing everything. Because of all these properties, life on Earth is intimately dependent on water. Every organism we know requires water to function. The chemical reactions that power metabolism, that build proteins and nucleic acids, that allow cells to grow and divide, all happen in water. We can imagine, in principle, life based on other solvents, perhaps liquid methane like on Saturn's moon Titan, or liquid ammonia. But we don't know if such life exists. The only life we know for certain requires water. So when astrobiologists search for life beyond Earth, they follow the water. Where there's liquid water, there's at least the possibility of life, and Europa has water, lots of it. In fact, despite being a small moon, Europa may contain more liquid water than all of Earth's oceans combined. The evidence for this is so compelling that it's now accepted as fact by planetary scientists. Europa almost certainly has a global ocean of liquid water beneath its icy shell. The question is not whether the ocean exists, but rather how deep it is, how thick the ice is, and what conditions exist in that hidden sea. The first clue to Europa's ocean came from simply measuring the moon's size and mass, calculations that yield its density. Europa's average density is about 3 grams per cubic centimetre, similar to Earth's moon. That density is consistent with a body made of silicate rock and metal in the interior, but significantly less dense than if it were solid rock all the way through. The density suggests that a substantial fraction of Europa's volume is made of something lighter than rock. The most likely candidate is water, either as liquid or ice. But density alone doesn't tell us if that water is liquid or frozen. For that, we needed closer observations, and we got them in the late 1990s when NASA's Galileo spacecraft arrived at Jupiter. Galileo orbited Jupiter for 8 years, from 1995 to 2003, and made multiple close flybys of each of the Galilean moons. The data it gathered transformed our understanding of these worlds, and especially of Europa. One of Galileo's most important discoveries came from its magnetometer, an instrument designed to measure magnetic fields. As Galileo flew past Europa, the magnetometer detected something unexpected and intriguing. Europa appeared to have a magnetic field, but not a permanent one like Earth's magnetic field, which is generated by the motion of molten iron in Earth's outer core. Europa's field was different. It was what's called an induced magnetic field, a secondary field created in response to Jupiter's own powerful magnetic field. Jupiter's magnetic field is enormous, the strongest planetary magnetic field in the solar system, about 20,000 times stronger than Earth's. And it rotates with Jupiter, sweeping over Europa every 11 hours as Jupiter spins. This changing magnetic field induces electrical currents in any electrically conductive material inside Europa, and those currents, in turn, generate their own magnetic field. That's what Galileo detected. But here's the key. For this to work, Europa must contain a large volume of electrically conductive material relatively close to its surface. Europa is too small and too cold to have a molten metallic core like Earth. Its rocky interior is probably solid. So, what could the conductive material be? The answer is salt water. Liquid water by itself doesn't conduct electricity very well. Pure water is actually an excellent insulator. But when you dissolve salts in water, the ions, the charged atoms or molecules that result when salts dissociate in water, can carry electrical current. Salt water is a good conductor, and the magnetometer data from Europa is consistent with a global layer of salty, electrically conductive liquid water beneath the ice shell, probably within 100 kilometers or so of the surface. This was a stunning revelation. Based on magnetic field measurements, Europa almost certainly has an ocean of salt water, but the evidence doesn't stop there. When we look closely at Europa's surface, at the high-resolution images captured by Galileo and later by the Hubble Space Telescope, we see a surface that tells a story of ice and water and geological activity. Europa is one of the smoothest objects in the solar system. Unlike most moons and rocky planets, which are heavily cratered from billions of years of impacts, Europa has very few craters. This tells us that Europa's surface is young, geologically speaking. Something is resurfacing Europa, erasing the scars of impacts. The best estimates suggest Europa's surface is less than 90 million years old, and some regions might be much younger, perhaps only a few tens of millions of years old, or even less. What we see instead of craters is a complex network of cracks and ridges called lineae. These features crisscross Europa's surface in every direction, some extending for thousands of kilometers. They look like cracks in ice, because that's almost certainly what they are. The ice shell has fractured, pulled apart in some places, pushed together in others. Some of the cracks appear to have dark material filling them, as if something from below, perhaps slushy ice or even liquid water mixed with minerals, has filled the crack and then refrozen. There are also regions of what's called chaos terrain, areas where the surface appears to have broken into blocks that have rotated, tilted, and shifted before refreezing into new positions. Imagine a frozen lake, where the ice has broken up into large rafts that bump against each other and then refreeze. That's what chaos terrain looks like, except on a planetary scale, with blocks the size of cities or small countries. The implication of these features is profound. Europa's ice shell is not static and frozen solid for all time. It's geologically active. It cracks, shifts, and renews itself. And the most plausible explanation for this activity is that there's liquid water, or at least warmer, softer ice, beneath the surface, allowing the upper ice to move and deform. Then there's the colour. Most of Europa is a brilliant white, the colour of clean water ice. But some features, particularly the lineae and some of the chaos regions, have a reddish or brownish tint. Spectroscopic analysis, studying the wavelengths of light that Europa's surface reflects and absorbs, suggests that this coloration might be due to salts and other minerals, possibly magnesium sulfate, sodium chloride, which is common table salt, and other compounds. Where did these salts come from? The most likely explanation is that they came from Europa's ocean. If liquid water from the ocean occasionally reaches the surface through cracks or volcanic-like activity, it would bring dissolved salts with it. When the water freezes or evaporates in the vacuum of space, the salts would be left behind, concentrated on the surface. The presence of these salts is further evidence that liquid water, and specifically an ocean containing dissolved minerals, exists beneath Europa's ice. And then there are the plumes. This is some of the most tantalizing, though still somewhat uncertain, evidence we have. In 2012, astronomers using the Hubble Space Telescope observed what appeared to be plumes of water vapor erupting from Europa's surface. The observations showed absorption of ultraviolet light in a pattern consistent with plumes of water reaching heights of over 100 miles above Europa's surface before falling back down. These observations have been repeated several times since then, though not consistently. The plumes, if they're real, seem to be intermittent rather than continuous. They might be associated with particular locations on Europa's surface, possibly with cracks or other geological features. And they might vary in strength depending on Europa's position in its orbit around Jupiter, suggesting that tidal stresses might play a role in opening and closing vents. If Europa is indeed occasionally venting water from its subsurface ocean into space, that's extraordinary news for several reasons. First, it confirms direct communication between the ocean and the surface. Second, it means we might be able to sample Europa's ocean without even landing on the surface. A spacecraft could fly through one of these plumes and collect particles for analysis, just as the Cassini spacecraft did at Saturn's moon, Enceladus, which also has water plumes. All of this evidence, the density, the induced magnetic field, the young and geologically active surface, the presence of salts that likely came from an ocean, and the possible water plumes, all points to the same conclusion. Europa has a global ocean of liquid, salty water beneath its ice shell. Current estimates, based on modelling and the various lines of evidence, suggest this ocean is probably about 40 to 100 miles deep, with an ice shell above it that's probably 10 to 20 miles thick, though these numbers are still uncertain. To put that in perspective, Earth's oceans average about 2.5 miles deep. Europa's ocean might be 40 or 50 miles deep, or even more. And because Europa's surface area is about 15% that of Earth, its ocean volume could be twice that of all Earth's oceans. It's a vast, global sea, wrapped in ice, orbiting a giant planet. But here's the crucial question, and it's the question at the heart of our exploration tonight. Just because Europa has liquid water doesn't automatically mean it has life. Water is necessary for life as we know it, but it's not sufficient. Life also needs energy, and it needs the right chemical ingredients, the raw materials that can be assembled into the complex molecules of biology. So let's think about where Europa's ocean gets its energy, and whether that energy could support life. Europa doesn't receive much energy from the Sun. At Jupiter's distance, about 5 times farther from the Sun than Earth is, sunlight is only about 4% as bright as it is here. And none of that feeble sunlight reaches Europa's ocean through the thick ice. So solar energy is essentially off the table. But Europa has other sources of energy, and the primary one is tidal heating. This is a beautiful and subtle process, and it's worth understanding because it's absolutely crucial to making Europa habitable. Europa orbits Jupiter, and Jupiter's gravity is immense. If Europa were the only moon, it would settle into a circular orbit and a stable, spherical shape. The side of Europa facing Jupiter would experience slightly stronger gravity than the far side because it's closer. But that difference would just create a permanent bulge on Europa, aligned with Jupiter, and that would be that. But Europa is not alone. It shares the Jovian system with 3 other large moons, particularly Io, which orbits closer to Jupiter than Europa, and Ganymede, which orbits farther out. And these 3 moons, Io, Europa, and Ganymede, are locked in a precise mathematical relationship called orbital resonance. For every orbit that Ganymede makes around Jupiter, Europa makes exactly 2 orbits, and Io makes exactly 4 orbits. This 1:2:4 ratio means that the moons regularly align with each other in predictable configurations, and when they align, their gravitational pulls on each other add up. These periodic tugs from the other moons keep Europa's orbit slightly elliptical rather than perfectly circular. An elliptical orbit means that Europa's distance from Jupiter changes as it orbits. When Europa is at its closest point to Jupiter, Jupiter's gravitational pull on it is stronger. When Europa is at its farthest point, the pull is weaker. This changing gravitational force continuously squeezes and stretches Europa, flexing it, deforming it, like kneading a ball of dough. And this constant flexing generates heat through friction. It's the same principle as bending a paperclip back and forth rapidly. The metal heats up at the bend point because the mechanical energy of bending is converted into thermal energy. Inside Europa, as the ice and rock flex and deform in response to Jupiter's changing gravity, that mechanical energy is converted into heat. This tidal heating is significant. Calculations suggest that tidal friction generates perhaps 100 terawatts of heat inside Europa, roughly equivalent to the power output of all of humanity's power plants combined. Some of that heat is conducted upward through the ice shell to the surface, where it radiates away into space. Some of it goes into melting ice at the base of the ice shell, replenishing the ocean. And some of it warms Europa's rocky interior. Europa also has some internal heat from radioactive decay. The rocky part of Europa contains small amounts of radioactive elements like uranium, thorium, and potassium, which decay over time and release heat. This is the same heat source that keeps Earth's interior molten and drives plate tectonics. Europa is smaller than Earth, so it has less radioactive material and generates less heat this way, but it's still a significant contribution. These two heat sources, tidal heating and radioactive decay, keep Europa's ocean liquid despite the moon being so far from the Sunday. And they might create conditions on Europa's ocean floor, similar to Earth's hydrothermal vents. If Europa's rocky mantle is in contact with liquid water, and if that mantle is being heated from below by tidal friction and radioactive decay, then water can circulate through the rock in a process called hydrothermal circulation. Cold seawater seeps down into cracks in the rock. Deep underground, it's heated by the hot rock, and it also reacts chemically with the minerals in the rock, a process called serpentinization. These reactions produce hydrogen gas and other reduced compounds, and they leach metals and other elements out of the rock and into the water. The heated water, now hot and chemically enriched, becomes buoyant and rises back up, eventually emerging from the seafloor at hydrothermal vents. As this hot, reduced, chemical-rich water mixes with the cold ocean water, it creates the same kind of chemical disequilibrium that we see at Earth's hydrothermal vents. And that disequilibrium is a source of energy that life could potentially tap into. So Europa likely has the same kind of chemical energy sources that support life in Earth's deep oceans. Hydrothermal vents on Europa's seafloor could provide heat, reduced chemicals like hydrogen and methane, and dissolved minerals. Microorganisms could use chemosynthesis to harness that chemical energy, building organic molecules and supporting an ecosystem. But there's another potential energy source on Europa, one that doesn't exist on Earth to nearly the same degree, and that's radiation from Jupiter. Remember that Jupiter's magnetic field bathes Europa in intense radiation. High-energy particles, mostly electrons and protons, slam into Europa's surface at tremendous speeds, millions upon millions of particles every second. This radiation is lethal to any surface life we can imagine. It would break apart complex molecules, shred DNA, destroy cell membranes. Nothing could survive on Europa's surface. But the radiation also has an interesting chemical effect on the ice. When these high-energy particles strike water ice, they break molecular bonds, splitting water molecules into their constituent atoms. Some of the hydrogen is light enough to escape Europa's weak gravity and drift away into space. But the oxygen and other oxidized compounds, like hydrogen peroxide and molecular oxygen, accumulate in the ice. Now, this is important. On Earth, most complex life, including all animals and plants, uses aerobic respiration. We breathe oxygen, and our cells use that oxygen as the final electron acceptor in a long chain of chemical reactions that extract energy from food. This process is much more efficient than anaerobic metabolism, which doesn't use oxygen. The evolution of oxygenic photosynthesis, which produces oxygen as a waste product, and the subsequent oxygenation of Earth's atmosphere and oceans, was probably crucial for the evolution of complex, multicellular life. Europa's surface is being bombarded with radiation that's creating oxidizers, molecules that can accept electrons. If those oxidizers could somehow make their way down into the ocean, either through cracks, or through the gradual turnover of the ice shell, or through plumes that cycle material between the surface and the ocean, then Europa's ocean might have both reducing compounds from hydrothermal vents and oxidizing compounds from the surface. That combination, reduced molecules that want to give up electrons and oxidized molecules that want to accept them, is a chemical battery. It's a source of energy. And if Europan life has figured out how to use both the oxidizers from above and the reduced compounds from below, then it might have access to the same kind of high-energy metabolism that powers complex life on Earth. That's speculative, and we don't know how much mixing actually occurs between Europa's surface and ocean, but it's an exciting possibility. So Europa has energy sources. It has tidal heating that keeps the ocean liquid and probably drives hydrothermal activity. It has chemical energy from reactions between water and rock. And it potentially has oxidizers produced by radiation. That's a rich menu of energy sources, more than enough, in principle, to support life. On Earth, the ultimate source of energy for most life is the sunday. Plants, algae, and photosynthetic bacteria capture sunlight and convert it into chemical energy stored in sugars and other organic molecules through the process of photosynthesis. This forms the base of almost every food chain on Earth. Herbivores eat plants, carnivores eat herbivores, decomposers break down dead organisms, and the energy that powers the whole system comes ultimately from the sunday. But Europa's ocean is dark. No sunlight penetrates through miles of ice. If there's life in Europa's ocean, it can't rely on photosynthesis. It must use some other source of energy. And remarkably, Earth has ecosystems that do exactly that. Ecosystems that thrive in complete darkness, independent of the sunday. These ecosystems were discovered relatively recently, and their discovery fundamentally changed how we think about the possibilities for life. In 1977, a team of scientists aboard the research submarine Alvin were exploring the ocean floor near the Galapagos Islands, in a region where tectonic plates are spreading apart and creating new seafloor. They were about 8,000 feet below the surface, well beyond the reach of sunlight, in a realm of perpetual darkness and crushing pressure. They expected to find a barren, lifeless landscape. Instead, they found one of the most remarkable ecosystems on Earth. Rising from the seafloor were hydrothermal vents, cracks in the rock, where superheated water, heated by volcanic activity beneath the ocean floor, came gushing out into the cold seawater. The water emerging from these vents, sometimes called black smokers because of the dark, mineral-rich plume they create, can be over 700 degrees Fahrenheit. That's hot enough to melt lead. And surrounding these vents, clustered around them in dense communities, was life. Giant tube worms, some over 6 feet long, with no mouth and no digestive system, their bodies encased in white tubes with brilliant red plumes waving in the current. Strange white clams and mussels, some the size of dinner plates, shrimp, crabs, and bizarre fish, all thriving in an environment that should, by all logic, be sterile and dead. How is this possible? How can life thrive here, in the dark, in the crushing pressure, near water hot enough to scald? The answer is chemosynthesis, a fundamentally different way of capturing energy compared to photosynthesis, but one that serves a similar purpose. The hot water coming out of hydrothermal vents is rich in reduced chemical compounds, molecules that have extra electrons and are eager to give them up. The most important of these are hydrogen sulfide, methane, and hydrogen gas. These compounds are produced by chemical reactions between the hot water and the rocks deep beneath the seafloor. When this chemical-rich water mixes with the cold, oxygenated seawater, there's a chemical imbalance, a disequilibrium. The reduced compounds want to react with oxygen to give up their electrons, and that reaction releases energy. Specialized microorganisms, bacteria, and archaea have evolved metabolic pathways to harness that chemical energy. They act as mediators, facilitating the reaction between the reduced compounds from the vents and the oxygen in the seawater and capturing the energy released. They use that energy to power their cellular processes and to build organic molecules from carbon dioxide dissolved in the water, just as plants build sugars from carbon dioxide in the air. Except instead of using light energy, they're using chemical energy. These chemosynthetic microorganisms form the base of the hydrothermal vent ecosystem. They are the primary producers, the organisms that convert inorganic matter and energy into organic matter that other organisms can use. Some animals at the vents feed directly on the microbes, grazing them off the rocks. But many of the larger organisms, including the giant tube worms, have formed intimate symbiotic relationships with chemosynthetic bacteria. The tube worms, for instance, have no mouth, no stomach, no way to eat in the traditional sense. Instead, their bodies are packed with billions of bacteria that live inside specialized organs called trophosomes. The worm provides these bacteria with a safe place to live and with access to the chemicals they need: hydrogen sulfide from the vent and oxygen from the surrounding water, which the worm absorbs through its bright red plume. In exchange, the bacteria produce organic compounds that feed the worm. It's a perfect partnership, a merger of two organisms into a functional whole. The discovery of hydrothermal vent ecosystems was revolutionary because it proved that life doesn't need the Sunday. Life can thrive using only chemical energy from Earth's interior. And if life can do it on Earth, then perhaps it can do it elsewhere. Perhaps any world with liquid water, a rocky interior that can provide chemicals, and a source of heat to drive chemical reactions could potentially support life. Perhaps places like Europa, despite being far from the sun, despite having oceans locked beneath ice, could have their own version of hydrothermal vents, their own chemosynthetic ecosystems. Since the discovery at the Galapagos Rift, scientists have found hydrothermal vents all over Earth's ocean floors, in every ocean basin, at different depths and temperatures. Some vents are scorchingly hot, over 400 degrees Celsius. Others are more moderate, what scientists call warm vents or diffuse flows. Each type of vent hosts its own specialized community of organisms adapted to the specific conditions, and the diversity of life at these vents is extraordinary. Beyond the giant tube worms and clams, there are blind shrimp that swarm around the vents, their backs covered with bacteria. There are yeti crabs with hairy claws that they use to farm bacteria. There are scale worms and squat lobsters and peculiar fish called zoarcids. There are mats of bacteria so thick they look like snowdrifts on the seafloor. Every vent is like an oasis in the deep sea, a localized burst of life in an otherwise sparse environment. What's remarkable is how quickly these communities establish themselves. When new vents open up, either because of volcanic activity or tectonic movement, they're colonized within months or years. Larvae of vent organisms apparently drift through the deep ocean, carried by currents, waiting for the chemical signals that indicate a new vent has opened. When they detect those signals, they settle and establish a new community. It's a lifestyle adapted to a dynamic, unpredictable environment where vents can shut off as quickly as they opened. The existence of these ecosystems has profound implications for astrobiology. Before 1977, most scientists assumed that all life on Earth ultimately depended on the Sunday. The deep ocean was thought to be sustained by organic matter raining down from the sunlit surface waters, a kind of subsidy from the photosynthetic world above. But hydrothermal vent ecosystems are truly independent of the Sunday. They could exist on a planet with no atmosphere, no sunlight, no photosynthesis. All they need is liquid water, a rocky interior, and heat. Europa has all three. If Europa has hydrothermal vents, and most models suggest it probably does, then it could have the same kind of chemosynthetic ecosystems that thrive at Earth's vents. The organisms would be different, adapted to Europa's specific conditions, but the fundamental energy source and metabolic strategy could be the same. But life needs more than just water and energy. It needs the right chemical elements, the building blocks that can be assembled into the molecules of biology. On Earth, life is built from a specific set of elements, often abbreviated as CH-NOPs: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Carbon is especially important because of its chemical versatility. Carbon atoms can form stable bonds with up to 4 other atoms, and they can bond with each other to form chains and rings. This allows carbon to be the backbone of enormously complex molecules, like proteins, DNA, and lipids. Life as we know it is carbon-based chemistry. Does Europa have these elements? Hydrogen and oxygen are obviously abundant. Europa is covered in water ice, and water is 2 hydrogens and 1 oxygen. Sulfur is likely present in the form of sulfate salts detected on the surface. The reddish-brown coloration in some of Europa's surface features might be due to magnesium sulfate or other sulfur compounds. Carbon is harder to detect remotely, but it's a common element in the solar system. Comets and asteroids contain organic compounds, carbon-bearing molecules, and Europa has surely been hit by countless small impacts over its history, delivering organic material to its surface. Some of that material would have been mixed into the ice and potentially delivered to the ocean over time. Europa's rocky interior might also contain carbon compounds, minerals called carbonates, that form when carbon dioxide reacts with rocks in the presence of water. Nitrogen and phosphorus are also essential for life, though they're harder to detect on Europa from afar. Nitrogen is common enough in the solar system, often found as ammonia or nitrogen gas. Ammonia ice might be mixed with water ice in Europa's shell. Phosphorus is less common but still present in rocks as phosphate minerals. It would be surprising if Europa's interior didn't contain at least some nitrogen and phosphorus, given that these elements are found throughout the solar system. So the chemical ingredients for life are almost certainly present on Europa. The elements are there, the water is there, and the energy is there. From a purely chemical and physical standpoint, Europa has all the prerequisites for life as we understand it. But there's another question to consider. Could the ocean and the icy surface exchange materials? This is important because, as we discussed, the surface might have oxidizers produced by radiation, while the ocean floor might have reducing chemicals from hydrothermal vents. If these two environments are isolated from each other, then the ocean might lack the chemical diversity needed to support a robust biosphere. There are several ways material could be exchanged. First, the ice shell itself might be convecting, slowly turning over like a very sluggish lava lamp. Warm ice from the bottom of the shell, where it's in contact with the ocean, might rise toward the surface, while cold ice from the surface sinks down. Over millions of years, this could cycle material between the surface and the ocean. Second, there's evidence of cryovolcanism, ice volcanoes, on Europa. Those chaos terrains and some of the dark lineae might be places where slushy ice or even liquid water has erupted onto the surface from below. If water from the ocean occasionally reaches the surface this way, it would bring dissolved chemicals with it. And when fresh ice from the surface sinks or gets subducted, it would carry surface materials, including those radiation-produced oxidizers, down into the ocean. Third, impacts from comets and asteroids would punch through the ice shell, at least temporarily, potentially allowing exchange between the surface and ocean. Large impacts might even create temporary lakes of liquid water beneath the impact site, mixing surface and ocean materials. So there are mechanisms for exchange, though we don't know how efficient they are. Europa Clipper will help answer this question by studying the composition of surface materials and looking for evidence of recent ocean-to-surface or surface-to-ocean transport. There's also the question of nutrients. Even if Europa has all the right elements, are they in the right chemical forms and in sufficient concentrations to support a thriving biosphere? On Earth, certain elements, particularly iron, nitrogen, and phosphorus, are often limiting factors for life in the oceans. In some regions, adding small amounts of iron causes massive algae blooms because iron was the limiting nutrient. Europa's ocean might be similarly limited by certain nutrients. If the ocean is isolated from the rocky seafloor by a layer of ice, perhaps a layer of high-pressure ice that forms at great depth and insulates the ocean from the rock, then the supply of nutrients from the rocky interior might be cut off, leaving the ocean nutrient poor. This is speculation, but it's a concern that some scientists have raised. On the other hand, if there's direct contact between liquid water and rock, and if hydrothermal circulation is occurring, then the ocean would be continuously enriched with elements leached from the rocks. The concentration of nutrients might be low compared to Earth's oceans, but it might be enough to support microbial life. These are the kinds of questions that Europa Clipper will help address, not directly by analysing the ocean, but by gathering data that will constrain models of Europa's interior structure and chemical evolution. By measuring the ice thickness, the ocean depth, the salinity, and the surface composition, scientists can build better models of what conditions are like in Europa's ocean and whether they're conducive to life. And that brings us to the mission itself, the extraordinary spacecraft that's currently on its way to Jupiter to study Europa in unprecedented detail. On October 14th, 2024, NASA's Europa Clipper mission launched from Kennedy Space Center aboard a SpaceX Falcon Heavy rocket. It was a spectacular launch, the massive rocket lifting off in a pillar of flame, carrying one of the most ambitious planetary science missions ever conceived. Europa Clipper is huge, about the size of a basketball court, when its enormous solar panels are fully deployed. In fact, it's one of the largest planetary spacecraft NASA has ever built. Those massive solar panels, each about 46 feet long, are necessary because at Jupiter's distance from the Sun, sunlight is much dimmer than it is near Earth. The spacecraft needs a lot of surface area to collect enough sunlight to power its instruments and systems. The spacecraft itself is heavily shielded against radiation. Jupiter's radiation environment is brutal, and even though Europa Clipper won't be orbiting Europa directly, it will still pass through intense radiation belts during its flybys. The sensitive electronics are housed in a thick-walled vault made of titanium and aluminum, designed to protect them from the constant barrage of high-energy particles. Europa Clipper won't take a direct route to Jupiter. That would require too much fuel. Instead, it's using a technique called gravity assist, flying by Mars and then Earth to pick up speed. The spacecraft will swing past Mars in early 2025, using the planet's gravity to bend its trajectory and accelerate. Then it will come back past Earth in late 2025 for another gravity boost. These maneuvers, sometimes called gravitational slingshots, are a clever way to change a spacecraft's speed and direction without using fuel. After the Earth flyby, Europa Clipper will be on its way to Jupiter, arriving in April 2030 after a journey of about 5.5 years. That might seem like a long time, but in terms of interplanetary missions, it's actually relatively quick. The distance from Earth to Jupiter varies as both planets orbit the Sun, but at its closest, Jupiter is about 390 million miles away. At its farthest, it's over 600 million miles. Covering that distance, even with gravity assists, takes years. Once Europa Clipper arrives at Jupiter, it will fire its engines to slow down and enter into orbit around the giant planet. But this won't be a simple circular orbit. It will be a highly elliptical orbit, a long, stretched-out oval that brings the spacecraft close to Jupiter at one end and sends it far out into the Jovian system at the other end. And here's the clever part. The orbit is carefully designed so that Europa Clipper passes close to Europa on a regular basis. Over the course of the mission, which is planned to last about 4 years, the spacecraft will make 49 close flybys of Europa. Each flyby will bring the spacecraft as low as 16 miles above Europa's surface, close enough to get detailed measurements, but quick enough to minimize radiation exposure. During each flyby, which lasts only a few hours, all of Europa Clipper's instruments will be working furiously, gathering data. The cameras will snap high-resolution images. The spectrometers will measure the composition of the surface. The radar will probe the ice. The magnetometer and gravity instruments will make precise measurements. And if the spacecraft happens to fly through a plume, the particle and gas analyzers will sample it. Then, after the flyby, Europa Clipper will retreat to a safer distance, spending several days or weeks away from the intense radiation close to Europa. During this time, it will download all the data it collected back to Earth. The Earth, because of the distance, will receive that data delayed. At Jupiter's distance, radio signals, traveling at the speed of light, take 35 to 52 minutes to reach Earth, depending on where the planets are in their orbits. So mission controllers on Earth will be seeing data from flybys that happened an hour ago. Real-time control is impossible. The spacecraft has to be largely autonomous, able to execute its commands and deal with any problems on its own. Each flyby will target different parts of Europa. Some will fly over the equator, others over the poles. Some will observe the leading hemisphere, the side of Europa that faces forward as it orbits Jupiter, while others will look at the trailing hemisphere. This ensures comprehensive coverage of the Moon, building up a global map with different types of data. Europa Clipper carries 9 scientific instruments, and each one is designed to answer specific questions about Europa. Let's walk through them, because they're fascinating examples of how we've learned to study other worlds from afar. First, there are 2 camera systems. The Europa Imaging System, EIS, is a pair of wide-angle and narrow-angle cameras that will map Europa's surface in high resolution and in 3 dimensions. By taking images from slightly different angles during different flybys, The cameras can create stereo views that reveal the topography, the heights and depths of surface features. The narrow-angle camera can resolve details as small as about 1.5 feet across in the best images. That's extraordinary. We'll be able to see individual boulders, the texture of the ice, the fine details of cracks and ridges. The Europa Thermal Emission Imaging System, ETHEMIS, is an infrared camera that measures heat. It will create temperature maps of Europa's surface, looking for warm spots that might indicate recent geological activity or places where the ocean is closer to the surface. Even a difference of a few degrees could be significant. Then there are the spectrometers. The Mapping Imaging Spectrometer for Europa, MISE, will analyze the composition of Europa's surface by measuring how different materials reflect sunlight at infrared wavelengths. Different molecules absorb and reflect different wavelengths, creating unique spectral fingerprints. MISE will be able to identify salts, organic compounds, water ice, and other materials, and map where they're located on the surface. The Europa Ultraviolet Spectrograph, Europa UVS, does something similar but in ultraviolet light. It will study Europa's tenuous atmosphere and look for plumes by detecting the ultraviolet absorption of gases like water vapor, oxygen, and hydrogen. One of the most exciting instruments is REASON, the radar for Europa assessment and sounding, ocean to near surface. REASON is an ice-penetrating radar that will send radio waves down into Europa's ice shell and measure the echoes that bounce back. Different layers within the ice, pockets of liquid water, or the ocean itself will reflect the radar differently. If it works as hoped, REASON could tell us exactly how thick the ice is, reveal the internal structure of the ice shell, and maybe even detect the ice-ocean boundary. This kind of radar has been used on Earth, particularly in Antarctica and Greenland, to study ice sheets. But doing it at another world, from a moving spacecraft, at altitudes ranging from 16 miles to hundreds of miles, is a significant challenge. The radar has to be powerful enough to penetrate potentially dozens of miles of ice, sensitive enough to detect weak echoes, and sophisticated enough to distinguish between different types of returns. Europa Clipper also carries a magnetometer, MAG, which will make detailed measurements of Europa's induced magnetic field. By mapping how the magnetic field varies as Europa orbits Jupiter and as Jupiter's magnetic field sweeps over it, scientists can determine the depth, thickness, and salinity of the ocean. A deeper or saltier ocean will generate a stronger induced field. The Gravity Science investigation uses the spacecraft's radio link with Earth. By precisely measuring tiny changes in the radio signal's frequency as Europa Clipper flies past Europa, scientists can detect how Europa's gravity tugs on the spacecraft. These measurements reveal how mass is distributed inside Europa, helping distinguish between ice, water, and rock layers. There's SUDA, the Surface Dust Analyzer, a remarkable little instrument that can capture and analyze tiny particles. It has a detector that's essentially a target. When a dust particle hits it at high speed, the impact vaporizes both the particle and a tiny bit of the target, creating a small cloud of ionized atoms. An analyzer measures the masses of those ions, determining what elements and molecules were in the original particle. If Europa Clipper flies through a plume, SUDA will capture particles from that plume and tell us what they're made of. And there's MASSPEX, the MS spectrometer for planetary exploration, which analyzes gases. It will measure what molecules are present in Europa's thin atmosphere and, if the spacecraft flies through a plume, what gases are being vented from below. MASSPEX is sensitive enough to detect trace amounts of organic molecules, salts, and other compounds. Finally, there's the Plasma Instrument for Magnetic Sounding, PIMS, which studies the plasma environment around Europa, the charged particles that flow past the Moon as Jupiter's magnetic field sweeps by. This helps characterize the interaction between Europa and Jupiter's magnetosphere. Together, these 9 instruments will give us an unprecedented view of Europa. We'll see the surface in exquisite detail. We'll map its composition and temperature. We'll probe the interior with radar. We'll measure the ocean's properties through magnetic and gravity studies. And we'll sample the thin atmosphere and any plumes. It's the most comprehensive study of an ocean world beyond Earth that's ever been attempted. The mission's primary science objectives reflect the key questions about Europa's habitability. First, to determine the thickness of the ice shell and how the ice and ocean interact. Second, to investigate the composition of the ocean and surface, looking for the chemicals necessary for life and for any signs of interesting organic chemistry. Third, to characterize the geology, understanding where the surface is most active and where future missions should target. Europa Clipper is not explicitly a life detection mission. It's not carrying instruments specifically designed to identify living organisms or the unambiguous chemical signatures of life. That's a much harder problem that would require either bringing samples back to Earth or sending a sophisticated lander with life detection instruments. But Europa Clipper will assess habitability and search for the conditions and chemistry that could support life. If the mission finds complex organic molecules, unusual isotopic ratios, chemical disequilibrium, or other intriguing chemistry, especially in plume samples, that would be a strong hint that something interesting is happening in Europa's ocean. It wouldn't be proof of life, but it would make the case for a follow-up mission even more compelling. Finding signs of life, or even hints of the right conditions for life, is extraordinarily challenging. We need to think carefully about what we mean by biosignatures, the signs that life might exist or might have existed. On Earth, living organisms leave traces. They alter their environment in characteristic ways. They produce certain molecules that are rare or absent in non-biological settings. They create patterns and structures. They preferentially use certain isotopes of elements like carbon, nitrogen, and sulfur. Let's think about isotopes for a moment. Most carbon in the universe is carbon-12, meaning the nucleus has 6 protons and 6 neutrons. But about 1% of carbon is carbon-13, with an extra neutron. Chemically, these two isotopes behave almost identically. Almost, but not quite. Carbon-12 is slightly lighter and reacts slightly faster in chemical reactions. Living organisms, because they use enzymes that speed up specific reactions, tend to preferentially use carbon-12 over carbon-13. The result is that organic matter produced by life is slightly enriched in carbon-12 compared to inorganic carbon. This difference is small, just a few percent, but it's measurable with sensitive instruments, and it's a potential biosignature. If we found organic molecules on Europa with an isotopic ratio that suggests biological processing, that would be intriguing evidence. But here's the challenge. We have to be absolutely certain that the isotopic ratio couldn't be produced by non-biological processes. Some chemical reactions, particularly at different temperatures or pressures, can also fractionate isotopes. So finding the right isotopic ratio is suggestive, but not definitive proof. The same is true for organic molecules themselves. Organic simply means carbon-based. It doesn't necessarily mean biological. There are many ways to produce organic molecules without life. Comets and asteroids are full of organic compounds produced by non-biological chemistry in space. Hydrothermal systems can produce simple organic molecules from inorganic starting materials. So finding organic molecules on Europa would be interesting, but it wouldn't automatically mean life exists there. What would be more compelling is finding complex organic molecules, particularly ones that are hard to make without biology. Amino acids, for instance, are the building blocks of proteins. There are hundreds of possible amino acids, but life on Earth uses only about 20 of them, and life on Earth exclusively uses left-handed amino acids. If we found amino acids on Europa with a strong preference for left-handed forms, particularly the same amino acids that Earth life uses, that would be suspicious. It could indicate life, or it could indicate contamination from Earth, which is why planetary protection is so important. Lipids, the molecules that make up cell membranes, would be another intriguing find. Certain types of lipids are essentially unique to biology. If we found those on Europa, it would be hard to explain without invoking life. Or consider something like ATP, adenosine triphosphate, the molecule that all Earth life uses to store and transfer energy. ATP is a complex molecule that's essentially never found outside living cells or the recent remains of living cells. Finding ATP on Europa would be pretty much a smoking gun for life. But realistically, Europa Clipper is unlikely to detect anything that's definitive. The instruments are sensitive, but they're taking measurements from a distance or analyzing tiny samples. What's more likely is that the mission will find hints and clues, tantalizing suggestions that something interesting is happening in Europa's ocean, and those hints will guide future missions. There's also the question of what Europan life, if it exists, might look like. Almost certainly, it would be microbial. The conditions in Europa's ocean, while potentially habitable, are not conducive to complex multicellular life. The ocean is dark, probably cold by Earth's surface standards, and likely nutrient-poor compared to Earth's sunlit oceans. These are the conditions that, on Earth, support microbial ecosystems but not complex organisms. But microbial doesn't mean simple, at least not in terms of biochemistry. Microorganisms can have extraordinarily complex metabolisms, sophisticated sensing and signaling systems, and impressive adaptations to extreme environments. A microbial ecosystem on Europa could be diverse and intricate, with different species specializing in different chemical reactions, competing for resources, forming symbioses, evolving and adapting over billions of years. Would Europan life use DNA? Would it have cells with membranes? Would it use proteins and enzymes? These are open questions. Life as we know it uses a particular set of molecular tools: DNA for information storage, RNA for information transfer, proteins for structure and catalysis, lipids for membranes. But is that the only way to do it? Some scientists think that DNA and the genetic code are probably universal, or at least very common, because they're so well suited to their functions. DNA is stable, it can store large amounts of information, and the double helix structure allows it to be copied accurately. The genetic code, the mapping between three-letter DNA sequences and amino acids, seems to have some error correction properties built in. Maybe any life anywhere would converge on something similar. But others think that's too Earth-centric. Maybe life on Europa uses a completely different information storage molecule. Maybe it uses different amino acids, or doesn't use amino acids at all. Maybe its membranes are made of something other than lipids. Maybe it has a fundamentally different cellular architecture. If we found life on Europa, and it turned out to be radically different from Earth life, that would be extraordinary. It would vastly expand our understanding of what life can be. It would tell us that biology is not constrained to a single solution, but can explore many different paths, and it would make the universe seem even more diverse and interesting. On the other hand, if Europan life turned out to be similar to Earth life, that would raise different questions. Are Earth and Europa's biospheres related? Did life originate on one world and get transported to the other? Or did life originate independently on both worlds, but converge on similar solutions because those solutions are, in some sense, optimal? There's also the possibility, which we have to consider, that there's no life on Europa. Maybe despite having all the right ingredients, life simply never emerged there. The origin of life, the transition from non-living chemistry to living biology, is still one of the biggest mysteries in science. We don't fully understand how it happened on Earth, and we certainly don't know how common or difficult it is. Maybe life requires not just the right ingredients and energy, but also very specific conditions or sequences of events. Maybe there needs to be a particular kind of chemical cycling or a certain kind of environment with specific properties. Maybe Europa has almost everything needed for life, but not quite everything, and that one missing ingredient or condition makes all the difference. If Europa Clipper and follow-up missions search thoroughly and find no signs of life, that would be disappointing, but still scientifically valuable. It would tell us that habitability, as we define it, is not sufficient for life. It would force us to refine our understanding of what life requires. And it would raise the probability that life is rare in the universe, which has its own profound implications. Let's step back and think about the broader context of this search. Europa is not the only place beyond Earth where we might find life. Mars has been a focus of astrobiology for decades. The planet clearly had liquid water on its surface billions of years ago. We can see ancient river valleys, lake beds, even what might be ancient ocean basins. If Mars was warm and wet in its distant past, then perhaps life emerged there. And if it did, perhaps some of it survives in subsurface environments, sheltered from the harsh surface conditions. Several Mars missions have searched for signs of past or present life, with mixed results. The Viking landers in the 1970s performed experiments that gave ambiguous results, some suggestive of biology, but also explainable by unusual chemistry. The Curiosity and Perseverance rovers have found organic molecules and evidence of ancient environments that could have supported life, but no definitive biosignatures. The search continues, and future missions, including potential sample return missions, will bring Martian rocks back to Earth for detailed analysis. Then there's Enceladus, Saturn's small moon that has captured scientists' imaginations. Like Europa, Enceladus has a subsurface ocean beneath an icy shell. And unlike Europa, Enceladus definitely has active plumes. The Cassini spacecraft flew through these plumes multiple times and analyzed their composition, finding water vapor, salts, and intriguingly, organic molecules, including complex hydrocarbons. The plumes on Enceladus appear to be more vigorous and more consistent than the possible plumes on Europa, making Enceladus another prime target for astrobiology. Enceladus is smaller than Europa, only about 300 miles across, but its ocean seems to be in direct contact with a rocky core, creating the possibility of hydrothermal activity. Some of the organic molecules detected in the plumes could be consistent with hydrothermal chemistry. Future missions to Enceladus could fly through the plumes with more sophisticated instruments, perhaps even detecting amino acids or other biomolecules if they're present. And then there's Titan, Saturn's largest moon, a world unlike any other in the solar system. Titan has a thick atmosphere, thicker than Earth's, composed mostly of nitrogen with some methane. It has weather, with clouds and rain and wind. And it has lakes and seas on its surface, not of water, but of liquid methane and ethane. Titan is cold, minus 180 degrees Celsius at the surface, too cold for liquid water. But liquid methane could potentially serve as a solvent for a completely different kind of biochemistry. Could there be life in Titan's methane lakes? It seems unlikely, but we can't rule it out. Methane doesn't have the chemical properties that make water such a good solvent for complex chemistry, but maybe life could work around that. Some scientists have speculated about organisms that use methane as a solvent, that breathe hydrogen instead of oxygen, that have membranes made of nitrogen compounds instead of lipids. It would be truly alien biochemistry, nothing like life on Earth. Titan also has a subsurface ocean of liquid water deep beneath its icy crust. So Titan actually has two potentially habitable environments: the surface, with its methane lakes, and the deep subsurface ocean. NASA is planning a mission called Dragonfly, a rotorcraft that will fly around Titan's surface in the 2030s, studying the chemistry and looking for signs of prebiotic or biological processes. Beyond our solar system, the search for life extends to exoplanets, planets orbiting other stars. We've discovered thousands of exoplanets over the past few decades, and many of them are in their star's habitable zone, the region where temperatures could allow liquid water on the surface. Some of these exoplanets might be ocean worlds, covered entirely by deep oceans with no land. We can't yet study these exoplanets in enough detail to search for biosignatures, but that's changing. The James Webb Space Telescope and future missions, like the proposed Habitable Worlds Observatory, will be able to analyze the atmospheres of exoplanets, looking for gases that might indicate life. Oxygen and methane together, for instance, would be hard to explain without biology because they react with each other. Life on Earth continuously replenishes both gases, maintaining them in disequilibrium. But Europa remains special because it's close enough to study in detail. It's within reach of our current technology. We can send spacecraft there, we can measure its properties, we can potentially sample its ocean through plumes. Within our lifetimes, we might actually know whether life exists on Europa. That's extraordinary. Think about what it would mean, personally, to know that life exists elsewhere. For some people, it might challenge deeply held beliefs about humanity's unique place in creation. Many religious traditions teach that humans are special, created separately, the pinnacle of divine creation. Discovering life on Europa wouldn't necessarily contradict those beliefs. Many theologians and religious scholars have thought deeply about how their traditions would accommodate the discovery of extraterrestrial life, but it would certainly require some theological reflection and adaptation. For others, finding life on Europa would be profoundly reassuring. The universe is vast and ancient, and we're tiny and recent. The thought that we might be utterly alone, the only consciousness in an incomprehensibly huge cosmos, can feel isolating and even terrifying. Knowing that life exists elsewhere, even if it's just microbes on an icy moon, would tell us we're part of something larger, that life is a natural and perhaps common feature of the universe. And it would change how we see ourselves. Every major scientific revolution has decentered humanity. Copernicus showed we're not at the center of the solar system. Later astronomers showed the sun is not at the center of the galaxy, and the galaxy is not at the center of the universe. Darwin showed that humans are not separate from nature, but evolved from earlier forms of life. Discovering life on Europa would be another step in that progression, showing that life itself is not unique to Earth, that biology is a universal phenomenon. There are practical implications too. Studying life in extreme environments, whether on Earth or other worlds, advances our understanding of biology and could lead to biotechnology applications. Organisms from Europa's ocean, if they exist, might have unique biochemistry that could inspire new medicines, enzymes, or materials. The search for life drives technological development in instrumentation, robotics, and data analysis, advances that have applications far beyond space exploration. And there's the inspiration factor. Space exploration, and particularly the search for life, captures imaginations. It inspires young people to pursue careers in science, technology, engineering, and mathematics. It gives us goals that require international cooperation and long-term thinking. It reminds us that we're explorers, that there are still frontiers, still mysteries to solve, still great questions to answer. But we also need to think about our responsibilities. If we find life on Europa, we have an obligation to protect it. Planetary protection, the effort to prevent contamination of other worlds with Earth life, is a serious concern. Europa Clipper was carefully sterilized before launch, but perfect sterilization is impossible. There's always some risk that hardy microbes, perhaps bacterial spores, could survive the cleaning process and make the journey to Europa. If those microbes somehow reached Europa's ocean and found it hospitable, they could potentially displace native life. Earth microbes, even extremophiles, adapted to harsh environments, have been evolving on Earth for billions of years, optimized for Earth conditions. Europan life, if it exists, would be adapted to Europa conditions. We don't know which would outcompete the other, but the risk of harming or destroying an alien biosphere is something we need to take seriously. This becomes even more important if we plan to send landers or drilling missions. A lander sitting on Europa's surface is one thing, but a probe that drills through the ice and enters the ocean is a direct pathway for contamination. Future missions will need even more stringent planetary protection measures, perhaps including terminal sterilization right before the probe enters the ocean, or using techniques that ensure any Earth microbes that make it to the ocean are dead. There's also the question of back contamination, bringing samples from Europa back to Earth. If we eventually retrieve samples of Europa's ocean and bring them back for detailed analysis, we need to ensure they're contained so that any Europan life doesn't escape into Earth's environment. This is probably a low risk. Any Europan organisms would be adapted to very different conditions and unlikely to survive on Earth, but it's not zero risk. The samples would need to be handled in high-level containment facilities, similar to those used for dangerous pathogens. These might seem like far future concerns, but they're being discussed now. The scientific and ethical frameworks for studying potential alien life need to be developed before we actually encounter it, not after. International agreements, protocols for handling samples, guidelines for missions, all of these are being worked out by committees of scientists, ethicists, and policymakers. And there's a deeper ethical question. Do we have the right to study Europa at all? Does a potential biosphere have intrinsic value, independent of any benefit to humanity? If Europa has life, is it ethically acceptable to disturb that life, even in the name of scientific knowledge? These are not easy questions, and different people will have different answers based on their values and philosophical frameworks. Some would argue that the pursuit of knowledge is a fundamental human good, that understanding whether we're alone in the universe is worth the small risks involved. Others might argue for a more cautious approach, that we should observe from a distance and minimize our impact until we better understand what we're dealing with. Most planetary scientists and astrobiologists fall somewhere in the middle, advocating for exploration but with careful safeguards. The current approach, which Europa Clipper follows, is to study Europa thoroughly from orbit and through flybys, minimizing the risk of contamination while maximizing scientific return. Future missions would be designed with even more care, perhaps using techniques like self-sterilizing entry probes or sample collection methods that minimize contact. It's worth noting that Europa has been hit by countless asteroids and comets over its history. Some of those impacts might have delivered organic compounds or even microbes from elsewhere in the solar system. If Earth and Europa have exchanged material via impacts, which is possible though unlikely, then Europa's ocean might already have been exposed to Earth microbes. But that natural process doesn't absolve us of responsibility. There's a difference between natural processes and deliberate human actions. As we think about these ethical considerations, it's also worth reflecting on what the search for life on Europa tells us about ourselves as a species. We're curious creatures, driven to explore and understand. We look at a frozen moon 400 million miles away and we wonder what's beneath the ice. We build spacecraft and instruments and send them across the solar system to find out. That curiosity, that drive to know, is one of the most distinctly human traits we have. But we're also capable of foresight and restraint. We can recognize that our actions have consequences, that we need to proceed carefully, that knowledge comes with responsibilities. The fact that we're having these conversations about planetary protection and ethics, that we're trying to develop frameworks for studying potential alien life responsibly, speaks well of us. The search for life on Europa is, in a sense, a test. Can we explore responsibly? Can we pursue knowledge while also being good stewards? Can we balance our curiosity with our obligations to protect what we find? The answers to these questions will shape not just how we study Europa, but how we approach the entire endeavor of searching for life in the universe. Imagine for a moment what it would be like if we found life on Europa. Picture the announcement: scientists standing at a press conference showing data from Europa Clipper or a follow-up mission, explaining that they've detected unmistakable signs of biological activity in samples from Europa's ocean. The news would spread around the world in minutes. It would be the lead story on every news outlet. Social media would explode with reactions, from excitement to skepticism to fear to wonder. And then what? What would change? In some ways, probably very little. We'd all still go to work, pay our bills, live our daily lives. The discovery of microbial life on Europa wouldn't immediately affect most people's day-to-day existence, but in other ways, everything would change. We would know, with certainty, that we're not alone, that life is not unique to Earth, that the universe is a place where biology can emerge wherever conditions allow. The scientific implications would be profound and immediate. Whole new fields of study would open up. Comparative biology between Earth and Europa would become possible for the first time. We could study how life adapts to different environments, whether certain features of life are universal or contingent, how evolution works when starting from different initial conditions. The discovery would energize astrobiology and make the search for life elsewhere even more urgent. If life emerged independently twice in one solar system, then the universe must be teeming with life. The focus would shift from, is there life out there, to how common is life and how diverse is it? Missions to Enceladus, Titan, and other potentially habitable worlds would be prioritized. The search for biosignatures on exoplanets would intensify. There would be philosophical and even spiritual reverberations. Different cultures and belief systems would process the news in different ways. Some would see it as confirmation that life is a fundamental property of the universe, perhaps part of a divine plan. Others might see it as evidence that the universe is purely material, that life arises naturally from chemistry without need for supernatural intervention. Many people would find the discovery deeply meaningful, a reminder that we're part of a cosmos that's richer and more interesting than we imagined. And there would be questions, so many questions. What does Europan life look like at the cellular level? How does it reproduce? What's its metabolism? How did it originate? How long has it existed? Has it evolved and diversified, or has it remained simple? Is it related to Earth life in any way? Could life be exchanged between Earth and Europa, or did they originate completely independently? Some of those questions might be answerable with remote observations and sample analysis. Others would require going there, sending submarines into Europa's ocean, exploring the seafloor, observing the organisms in their native environment. That kind of mission is decades away at least, but the discovery of life would make it a priority. And what if we found no life? What if Europa Clipper and follow-up missions searched thoroughly, sampled plumes, analyzed the ocean's chemistry, and found no evidence whatsoever of biology? That would also be significant. though disappointing. It would tell us that habitability, as we understand it, is not sufficient for life, that something else is required, something we don't yet understand or haven't considered. It might mean that the origin of life is much rarer than we hoped, that it requires not just the right conditions but also an extraordinary stroke of luck, a series of improbable events that might happen only once in a billion worlds. If that's the case, then we might truly be alone, or at least very isolated, in a universe that has the ingredients for life, but rarely manages to actually produce it. Or it might mean that Europa is missing some crucial ingredient or condition that we haven't identified. Maybe the ice shell is too thick, preventing the necessary exchange between the surface and ocean. Maybe the ocean doesn't have enough of certain key nutrients. Maybe the chemistry is subtly wrong in some way that precludes biology. Understanding why life doesn't exist on Europa, if indeed it doesn't, would be almost as valuable as finding life, because it would teach us what life truly requires. But let's be optimistic. Let's imagine that the answer is yes, that there is life on Europa, that in the dark ocean beneath the ice, microorganisms cluster around hydrothermal vents, harvesting chemical energy, growing, reproducing, evolving. Imagine that they've been there for billions of years, since shortly after Europa formed, an entire biosphere cut off from the rest of the universe, hidden beneath the ice, unaware of the stars, unaware of Earth, unaware that anyone is searching for them. There's something poetic about that image. Life in darkness, persisting not because of the sun, but because of the heat from Europa's interior and the chemical energy available at the seafloor. Life that never knew daylight, never saw the sky, and yet found a way to exist and continue. And somewhere on that same Europa, in orbit around it, there would be a spacecraft. Europa Clipper, built by humans on Earth, sent across 400 million miles, carrying instruments designed to search for signs of that hidden life. The spacecraft doesn't know what it's looking for, not really. It's just following its programming, making measurements, sending data back to Earth. But that data is being analysed by scientists who very much want to know, who are driven by curiosity and wonder, who have dedicated their careers to answering the question of whether we're alone. That's where we are right now. Europa Clipper is on its way. In April 2030, it will arrive at Jupiter and begin its mission. For the next 4 years, it will fly by Europa dozens of times, gathering data that will tell us more about this mysterious moon than we've ever known. And somewhere in that data, there might be hints, clues, suggestions that life exists in the ocean below. We don't know what we'll find. Maybe Europa is teeming with life, maybe it's sterile. Maybe the truth is somewhere in between, with life present but sparse, or extinct life leaving only chemical traces. Whatever the answer, we're going to learn something profound about our universe and our place in it. There's a final thought worth considering. We've spent this evening talking about Europa, about its ocean and its potential for life, about the missions we're sending and the questions we're asking. But in a deeper sense, we've been talking about ourselves, about humanity and what drives us. We're a species that looks up at the night sky and wonders what's out there. We're a species that sees a distant moon and asks whether it could harbour life. We're a species that builds spacecraft and sends them across the solar system, not for any immediate practical benefit, but because we want to know. That curiosity, that desire to understand, is perhaps one of the most fundamentally human characteristics we have. And we're living in an extraordinary time. For all of human history, the question of whether we're alone in the universe has been purely philosophical, a matter of speculation and belief. But now, for the first time, we have the tools to actually answer it. We can go to other worlds and look for life. We might not find it tomorrow, or even in the next decade, but we're looking. And whether we find life or find that we're alone, we'll know. That's a privilege that no previous generation has had. Europa, this frozen moon of Jupiter, might hold the answer to one of the deepest questions we've ever asked. Is life a cosmic imperative, emerging wherever conditions allow? Or are we unique, the only place in a vast universe where biology became consciousness? Europa can't tell us the full answer, but it might tell us enough to point the way. So as Europa Clipper makes its journey, as it approaches Jupiter and begins its mission, as it swoops low over Europa's cracked and ancient ice, remember that it's there because we wanted to know. Because somewhere in our nature as a species, alongside all our faults and failings, there's also wonder, curiosity, and the drive to understand our universe and our place in it. Next time you look up at the night sky on a clear evening, find Jupiter. It's usually one of the brightest objects in the sky, shining steadily while stars twinkle around it. And think about Europa, that small moon orbiting the giant planet, with its ocean hidden beneath the ice. Think about the possibility that in that cold, dark sea, life might exist, completely unaware of the stars, of Earth, of us. And think about the fact that we're searching for it, that right now there's a spacecraft on its way there, carrying our curiosity across the vast empty spaces between worlds. That's something worth marveling at. That's something worth staying awake for. Sleep well, wherever you are, and maybe dream of distant oceans and the life that might swim in them. Before we end our journey tonight, let's take one more moment to think about the bigger picture, about what all of this means, not just for science, but for us as individuals and as a civilization. The search for life on Europa is ultimately about understanding our context, about figuring out where we fit in the grand scheme of things. For most of human existence, we had no idea how vast the universe truly is. Ancient peoples could see the stars, but they had no way of knowing that each star is a sun like ours, potentially with its own planets. They had no way of knowing about galaxies, about the hundreds of billions of stars in our Milky Way, about the trillions of galaxies beyond it. The observable universe contains more stars than there are grains of sand on all of Earth's beaches. That's not hyperbole, that's a conservative estimate. And we now know that planets are common. Most stars have planets. Many of those planets are rocky worlds like Earth or icy moons like Europa. The sheer number of potentially habitable environments in the universe is staggering, perhaps billions in our galaxy alone, quadrillions or more in the observable universe. With numbers like that, it seems almost absurd to think that Earth is the only place where life has emerged. And yet, we don't know. We have a sample size of 1. Earth is the only place where we know for certain that life exists. That's why Europa matters so much. If we find life there, even simple microbial life, we'll have doubled our sample size. We'll know that life emerged at least twice in our solar system. And the statistical implications of that would be profound. Think about it this way. If life emerged independently on 2 worlds in a single solar system, that suggests life emerges readily given the right conditions. Our solar system is only about 4.5 billion years old. It's one of hundreds of billions of star systems in our galaxy. If life can emerge twice here, then life must be abundant throughout the galaxy. There could be millions or billions of worlds with life in the Milky Way alone. Of course, there's a big difference between simple microbial life and complex multicellular life, and an even bigger difference between complex life and intelligent, technological civilizations. Even if microbial life is common, intelligence might be rare. Earth has had life for at least 3.5 billion years, but intelligent, technological civilization has only existed for a few thousand years, a tiny fraction of Earth's history. Maybe the jump from simple cells to complex organisms is rare. Maybe the jump from complex life to intelligence is even rarer. This is the famous Fermi paradox. If the galaxy is billions of years old, and if intelligent life is possible, then even if it's rare, there should have been time for it to arise many times and spread throughout the galaxy. So where is everybody? Why haven't we detected any signals from alien civilizations? Why hasn't anyone visited Earth? There are many proposed solutions to the Fermi paradox. Maybe intelligent life is much rarer than we think. Maybe civilizations don't last long. They destroy themselves or go extinct before they can spread far. Maybe interstellar travel is too difficult, and civilizations stay confined to their home systems. Maybe they're out there but deliberately avoiding contact. Or maybe we're looking in the wrong ways or not listening carefully enough. Or maybe, and this is a sobering thought, maybe we're early. The universe is about 13.8 billion years old. The first generations of stars didn't have planets with the right chemistry for life because they lacked heavy elements. Those elements had to be created in stars and spread through supernova explosions. It took time for the universe to become a place where life could emerge. Maybe Earth is among the first worlds to develop intelligent life. Maybe, in a few billion years, the galaxy will be full of civilizations, but right now, we're among the pioneers. Finding life on Europa wouldn't directly answer these questions about intelligence and civilization. Europan life, if it exists, is almost certainly microbial. but it would tell us that life itself is common, and that's a start. It would tell us that we live in a living universe, one where biology emerges naturally from chemistry, where the potential for life is built into the fabric of reality. And that has implications for how we see ourselves and our responsibilities. If we're alone, or nearly alone, then in a sense the fate of life, at least in our corner of the galaxy, rests with us. If we destroy ourselves, if we fail to become a spacefaring species, if we go extinct, then maybe the universe loses something precious and rare. But if life is common, then the pressure is off in a way. Life will continue, elsewhere, even if we fail. But that doesn't mean we're off the hook ethically. If life is common, then so is the potential for suffering, for ecosystems being disrupted, for species going extinct. Our actions matter, whether we're alone or not, and if we're among the first intelligent species in the galaxy, then we have an opportunity, maybe even a responsibility, to set a good example, to show that intelligence can be compatible with wisdom and ethics. These are heavy thoughts, maybe too heavy for bedtime, but they're worth pondering occasionally, these big questions about life and intelligence and our place in the cosmos. The search for life on Europa connects to all of them. It's a piece of a much larger puzzle, one we're just beginning to put together. One more thing before we close. There's a beautiful symmetry to the fact that we're searching for life on Europa now, at this moment in history. The Europa Clipper mission launched in October 2024. It will arrive at Jupiter in 2030. By the mid-2030s, we might have answers, or at least strong hints, about whether Europa harbours life. That means that many of you watching this, especially if you're young, will likely live to see the answer. You'll witness, possibly, one of the most important discoveries in human history. That's extraordinary. Your children or grandchildren might grow up in a world where it's simply accepted fact that life exists on multiple worlds, where astrobiology isn't a speculative science, but a thriving field with actual alien organisms to study. Or you might witness the sobering realization that Europa, despite being apparently habitable, is lifeless. That would be disappointing but still fascinating, and it would reshape how we think about life's origin and prevalence. Either way, you're living through a pivotal moment in the human story, the moment when we stopped wondering whether we're alone and started finding out. So pay attention over the next few years. When Europa Clipper arrives at Jupiter in 2030, watch for the news. Read the scientific papers, if you're inclined. Look at the images that the spacecraft sends back. Follow the story as it unfolds. You're witnessing exploration in real time, the same spirit that drove ancient sailors to cross oceans and early astronomers to map the sky, but now extended to other worlds. And maybe, just maybe, we'll get an answer. Maybe the data will show clear signs of life, or clear signs of a lifeless ocean, or something ambiguous that sparks more questions. Whatever we find, it'll be real data from a real place, not speculation but actual observation. That's the power and beauty of science, that we don't just wonder and argue, we go and look. Europa is waiting, the spacecraft is on its way, and we get to see what happens next. What a time to be alive. As we come to the close of our time together tonight, let's return to that question we started with. What is life? We've explored Europa, its ocean, its energy sources, the missions we're sending. We've thought about hydrothermal vents and chemosynthesis, about biosignatures and the challenges of detecting life from afar. But underneath all of that is this fundamental question, this mystery that we still haven't fully solved. Life is complex organization that maintains itself against entropy. It's chemistry that has become so intricate, so finely tuned, that it can sense its environment, respond to it, preserve its structure, and make copies of itself. It's a temporary victory against the universe's tendency toward disorder, a localized reversal of entropy powered by energy from outside. But that definition, while accurate, doesn't capture the wonder of it. Life is also adaptation, evolution, diversity. It's the ability to solve problems, to find niches, to persist in the face of challenges. It's 3.5 billion years of trial and error on Earth, of organisms exploring every possible way to make a living, from photosynthesizing plants, to predatory animals, to bacteria that eat rock, to fungi that dissolve dead matter. Life is also, at least on Earth, connection. Every organism is connected to every other organism through the web of ecology and the tree of evolution. We share ancestors with every living thing, if you go back far enough. The bacteria in your gut, the trees outside your window, the birds in the sky, we're all cousins, all descendants of that first living cell that emerged billions of years ago. And life is fragile. Despite its resilience, despite its ability to adapt and survive, life is also precious and easily destroyed. Every species that goes extinct is a loss, a branch pruned from the tree of life, a unique solution to the challenges of existence that's gone forever. That's true whether we're talking about life on Earth or potential life on Europa. If there is life on Europa, it would be separate from Earth's tree of life. It would have its own history, its own evolutionary story, its own solutions to the problems of existence. It might share some features with Earth life because some solutions are universal, dictated by chemistry and physics, or it might be radically different, showing us that life can take paths we never imagined. Either way, it would be precious. It would be something to study with care and respect, something to protect, something to marvel at. The discovery of life on Europa wouldn't just be a scientific triumph. It would be a moral moment, a chance to show that we can be good stewards of the life we find. And if there's no life on Europa, then the search continues. Mars, Enceladus, Titan, the moons of Uranus and Neptune, the thousands of exoplanets we're discovering, all of them are potential homes for life. We'll keep looking, keep exploring, keep asking the question, because the question matters regardless of the answer. In a way, the search for life is the search for meaning. We want to know if we're alone because it tells us something about who we are and what our existence means. If we're alone, then we're cosmically rare, precious beyond measure, and the responsibility to preserve life rests heavily on our shoulders. If we're not alone, then we're part of a grand community of living worlds, each with its own story, and our responsibility is to be good neighbours, good citizens of the cosmos. Europa, with its hidden ocean and its tantalising hints of habitability, is where we might find our first answer. It's not the only place we're looking, but it's one of the best candidates we have. And the fact that we're looking at all, that we've built spacecraft and instruments and devoted careers and resources to this search, says something hopeful about humanity. We're not perfect. We have our conflicts and our failings, but we're also capable of wonder, curiosity, and cooperation. We can come together across national boundaries to explore the cosmos. We can ask profound questions and work patiently, for decades if necessary, to find answers. We can look at a distant moon and see not just ice and rock, but possibility, potential, a place that might harbour the most important discovery we ever make. So as you drift off to sleep tonight, carry that with you. The knowledge that somewhere out there, 400 million miles away, a moon orbits a giant planet. That moon has an ocean, deep and dark and cold, hidden beneath miles of ice. And in that ocean, there might be life. Simple life, microbial life, but life nonetheless. Organisms that have existed for billions of years in complete isolation, in eternal darkness, powered by chemistry and heat, evolving, adapting, persisting. And carry with you the knowledge that we're searching for that life. That a spacecraft built by humans is on its way there right now, crossing the vast distance between worlds, carrying our curiosity and our hope. That in a few years, we might have an answer to one of the oldest questions our species has ever asked. That's something worth wondering about. That's something worth staying curious about. And that's something that connects you to the broader human story, to the grand endeavour of understanding our universe and our place in it. Thank you for spending this time with me tonight. Thank you for wondering about Europa, about life, about the cosmos. Thank you for your curiosity and your open mind. And thank you for being part of this moment in history, this time when we're reaching out beyond our world to search for others like us. Next time you see Jupiter in the night sky, remember Europa, remember the ocean beneath the ice, remember that we're searching, and remember that the answer, whatever it is, will change everything. Sleep well, dream of distant oceans, hidden worlds, and the life that might swim in seas we've never seen, and wake tomorrow knowing that somewhere out there, the search continues.